All right, good afternoon, everyone. So today is our last class. We will finish what we discussed previously on the static fluids, and then we will move on to fluid dynamics. Um, Again, just wanted to remind you, our final exam is going to be on Tuesday on Blackboard for 3 hours, 25 questions, and the content will be heavily focused on the content we do after the second midterm, starting from rotational kinematics, rotational dynamics, um, angular momentum, conservation of angular momentum, and then gravitation, simple harmonic oscillation, and fluids.
What was the time for the test?
3 hours.
Oh, but I mean, from what time to what time, or is it 24-hour period?
Will be available for the entire 24 hours on Tuesday.
Okay, thank you.
Okay, and then so tomorrow I still have an extra office hour from 12 to 1:50. I combined it with my other class, so it would be a different link. I posted that link on Blackboard announcement. So if you have any questions you want to ask before the final, please come up tomorrow to ask questions, or on Tuesday of the finals day. I will open up my class Zoom chat in case you have any last minute questions. All right. Okay, let's get back to our class. So this is still talking about the Archimedes principle to calculate the upward force, the buoyant force that the any object is feeling when submerged in the liquid. Here we have an ice cube that is floating on the water. You notice 90% of a submerged volume is beneath the surface. Now, suppose we put the same ice cube, instead of putting it in water, we put it in other liquid that has a smaller density. So how much of the ice cube will be submerged? Now we know that the buoyant force an object feels is rho g times v. Rho is the density of the liquid, and g is 9.8 meters per second square, and v is how much volume is under the liquid, how much liquid is being displaced, right? So you need to provide that amount of force. So you can see that if you put it, no matter what liquid you put it in, you're going to provide a force that's equal to the weight of the ice cube, right? Because it was trying to stay afloat. So to provide the same amount of force, if you switch the liquid from water to something less dense, you are reducing rho. So if rho is smaller, and then to provide the same amount of force, rho g times v, you need to increase the volume in order for rho g v to still cancel out the weight of the ice cube, so that ice cube will stay afloat. So you can see that if it's in water, 90% of the ice cube is in water. So if something less dense, you need more than 90% of the volume in order to provide the same amount of force, right? So the answer would be A. That's the checkpoint question you have already seen. Speaking of how this principle was discovered, there is a very nice story saying that back in Archimedes' age, the king gave a goldsmith some gold to make a crown. By the time the crown was made, the king suspected maybe some silver was mixed in. Maybe it's not all gold. Maybe that the goldsmiths have taken some of the gold and kept it for themselves. So the king gave Archimedes a task. Can you figure out whether this crown was made of 100% gold, just like the gold I give to him, or is there some other material that's been mixed in? So that is the task, right? That he has to figure out. So he's trying to think very hard for it. One day he was taking a bath. He's still trying to think about the problem, but he also thought about the solution. While getting into the bathtub, Archimedes noticed the water was displaced. Of course, when we step into the water, we're displacing water, right? in an amount equal to his volume and figure out a way to determine the density of the crown. He was so happy he run out and shouted, "Eureka, Eureka," meaning that I found it. So what is the method he found to test for the density of the crown, whether it's actually made of gold, 100%. So this is the method. So he balanced the weight of the crown with pure gold in air. This is pure gold. So we know that the sort of the reference we're comparing the crown to has the same density as gold because it is pure gold. Okay, so these two are balanced. You can see they have the same weight. And then you dip them both in water. So they should also still be balanced if the crown was made of pure gold, right? Because if the crown was made of also the gold, the crown has the same volume as the bulk of gold. They're all the same mass, so they also have the same volume, which means they will displace the same amount of water, so that whatever you measure, the scale should still be level. However, if the crown is less dense, meaning that if you had mixed in some other material, most likely material that has a less density than gold, right? If you put in silver in it or anything other metal, then it's going to have a smaller density than gold. Then overall, the crown has a less density, which means with the same amount of mass, it must have a larger volume than what it would have been if it were a pure gold. So if it displaces more volume, then the crown will feel a bigger buoyant force up, giving more of a lift to the left-hand side so that the scale will no longer be level. That is using the Archimedes principle. And then did the experiment, and indeed the crown was actually did have a less dense density than the pure gold. The suspicion was true. There was indeed something mixed in the crown. That's the story behind the Archimedes principle. We can see that the density is now reflected when you put them in water. Okay, so this is a question from the homework. For this, I will switch back to a tablet, which allows me to write and solve the problem on paper. So just 1 second. 1 second. Okay, so this is the same question you were seeing. So we're trying to answer the first 3 questions of this homework problem together, okay? Okay, so you're given a U-shaped tube, and you filled these blue are water, and the yellow are the oil. The oil stays on top of the water. The height on the left-hand side is H1. The height on the right-hand side is H2 and H3. H2 are how high the water is. H3 is how high the oil is. We're given the atmosphere pressure, right, which is 101,300 Pascal. Give also the density of the water. What is the absolute pressure in the water at the bottom of the tube right here? So that is the first question. Well, this is really just a plug and check question. It's not too hard to calculate, right? Because we know how to calculate the density above, below the certain depth of the surface of the water. So we know that the pressure right here at this point, let's call it point B, is whatever at the atmosphere plus whatever this extra pressure caused by the weight of the liquid, which is rho GH, right? Rho GH. So the rho is water and H is H1. That's how high it is. So if you simply add that on top of the atmosphere pressure, give you the pressure you feel at the bottom of the tube. And this is 101,300 Pascal. And we can plug in the SI unit. We plug in SI unit for density and everything else. We will get a pressure that is the same unit as here, it's Pascal. So we need 1,000 kilograms over meter cubed times 9.8 meters per second square times 0.38 meters. So I'm using SI unit for everything. That gives me Pascal. So I get 3,724 Pascal and added onto the atmospheric pressure. So this is the final pressure that you feel at the bottom of the tube. Okay, so really just use this equation. And let's look at the second question. What is the absolute pressure in water right at the oil water surface? So what is the pressure over here? Okay, so you know that we just calculate the pressure here, right? Which means everywhere of the same dash line, everywhere at the bottom with the same pressure. So whatever the pressure over here, plus the extra pressure of the liquid give you the pressure at the bottom. So which means here, if you call the pressure at interface, right? The interface, the water and oil, plus the extra pressure rho GH2, this extra water, is going to be the pressure at the bottom. This one you already calculated, right? From your first part. And we can find the pressure at the interface to be pressure at the bottom minus rho GH2. Okay, and that is going to be 105.04 Pascal, which was the pressure at the bottom. And I can plug in all these numbers for 1,000 kilo per meter cubed for the density of the water times 9.8 for G times H2 is 0.12 meters. Okay, so overall you found this is going to be 103,848 Pascal. So for this one. So that is what the pressure is right here at the interface. Okay, so you can see we're still using the same equation. The last question is, what is the density of the oil? It's not given. Well, you can see there are two ways to figure out the pressure at the interface. One is starting from the bottom up, right? By minus the rho H2, or we can do it from the top down, which is using the pressure here at the atmosphere and multiply and plus rho GH3. So both of those methods should give me the pressure at the interface. So we just found out the pressure at the interface for the previous question. If we take the top down method, is the pressure at the atmosphere right here in the air plus rho of the oil GH3. So if you add the extra pressure caused by the yellow column, which is the oil, you get the pressure right here at the bottom of the oil column. So you can figure out the density from this equation, right? So oil is pressure of the interface minus the atmosphere pressure divided by G over H3. So you can plug in those numbers, which is about 839 kilograms per meter cubed. So which is smaller than the density of the water, right? Water is 1,000 kilo per meter cube, and oil is 839, which is smaller, as we expected. Okay, so you can see this is really just repeatedly using the equation of a pressure at any depth underneath water, the pressure here is the pressure of the atmosphere plus the extra pressure caused by the liquid, okay, by the weight of the liquid. So whichever liquid you're talking about, you use the density for that liquid. If it is water, you use density for water. If it is oil, you use the density of the oil. All right, so it's really just keep practicing this particular question equation.
There was a question with this particular part of the homework, and it was saying what was the pressure at the bottom when the oil was changed to something with a different density. How come it stayed the same even though the different oil was introduced?
And what is the bottom? What is the pressure at the bottom? Would they keep the H1 to be the same height?
No, that one changed.
And right, I gotta look at the question. Wait, hold on. See if I can answer it fairly quick. If not, I will have to answer your question outside of class. I'll send an announcement later. But let me take a quick look if we can get this question out of the way fairly quickly. And this is homework 14, right?
Yes.
Okay. YouTube, is it? I think so. Hmm. The question is by replacing the oil with some other height with a different material, and is asking what is the, okay, so firstly asking what is the absolute pressure in the water at the interface. So that one you said there's no problem?
Yeah, I was able to figure it out. I just didn't understand why it was that the pressure at the bottom stayed unchanged.
It doesn't have to be. I think they may give you they give you a particular height of the density so that the bottom stays unchanged. It doesn't have to be unchanged though. Imagine if you keep adding more and more water to the tube, of course you're increasing the pressure. I think it just so happens it remained the same, but it doesn't have to be remaining the same. Actually, I don't even know if it is unchanged. So, okay, so the original absolute pressure at the bottom is 104,831 Pascal. But now replacing the oil with some other material, now the absolute pressure in the bottom is 105 and 484. So it did change. It did change on my side of the solution. I don't know. Do you want to send, you can send your question to me later. I can look at it.
Okay.
Okay, so on my side, it does change. But you know, it's always just a repeatedly applying this particular equation. So there's nothing too much about problem solving involved for this type of questions. Okay, so far, what we have been talking about is all these fluids are sitting still. They're in static situation. They're not moving. Now we investigate flowing fluids. Now, noticing that in engineer fluid dynamics, it's its own course, right? There is a whole branch of study is focusing on studying flowing fluids. And obviously, there's no way we can teach you all of that in 30 minutes of the class. But we'll try to do our best to do a couple theories and provide sort of an overall review of what's going on. So of course we consider something called ideal fluids. What I mean ideal is that they are incompressible. Liquids is a good model for ideal fluids, but not gases are not ideal fluids because they're all compressible. Also, ideal fluids are non-viscous, which means there's no kinetic friction between the liquid parts. We're also considering ideal fluids with laminar flow, so there is no turbulence, like the picture showing, right? A steady flow instead of like a turbulence flow. So the theories we're going to talk about are applicable to the ideal fluid. Sometimes you may have to do a sort of a approximation, saying this is an approximate situation of what is really going on. There's also something called streamlines when we consider, for example, liquid like water flowing through a tube. You can imagine paths taken by particles in the fluids, right? Particle from going from here to there. And we call these paths to be streamlines. In the ideal fluid, the streamlines have two important properties. One is that they never cross, right? And another thing is fluid speed is higher when the streamlines are closer together. So this is sort of a tool that we use in physics. Sometimes we draw these field lines. For example, we draw field lines to describe an electric field. In 1520, you will see that we use these lines to represent the density of the line to represent the strength of the field, right? When closer the line together represent a higher value of something. In this case, for streamline lines, the more dense these lines are together, meaning that the speed of the flow is higher. Okay, so this is our just important properties that we have for streamlines. One of the important theories we will talk about is a continuity equation. Continuity equation is essentially something you see here for whatever comes in, comes out for liquid flow. In 1520, for the continuity equation, you will have continuity equation if you're dealing with electric charges when they're flowing. So the idea also carries over beyond this course to something another, to a different context. So what is the continuity equation for flowing fluids? For a steady flow, we say the amount of fluid entering point 1 in the time interval delta t must equal to the amount of fluid exiting point 2 in the time delta t. So that describes something is a steady flow. It's just like how if you think about if you have a hallway and people are constantly entering the hallway and also leaving the hallway to go to subsequent rooms like movie theater. People coming in from outside and also they go to different rooms to see different movies. So imagine if you have a steady flow of people, right? Meaning that there's always equal number of a constant number of people in the hallway at a time. There are always, let's say, 50 people. 20 more people coming in, but also at the same time, 20 more people went away from the hallway to see movies. So the total amount of people in the hallway is still the same. So this is sort of a similar analogy of describing what is called a steady flow, right? Whatever liquid comes in is equal to whatever liquid goes out of the area. So how do we describe that with mathematical expression? Let's consider an area with surface area A. And if that area of water is traveling at a speed v, so in time delta t, it will travel a total distance of v delta t. So that is the time. For a steady flow, the two volumes must be equal, right? The amount of water, so how do we describe the amount? Is volume. The amount coming in equals the amount goes out. So the volume coming in is equal to the volume going out in the equal amount of time. So you can see that a volume is area times the height. So area 1 times the height, D1 is equal to area 2 times the total height of D2. So these two volumes are the same. That is a steady, what means a steady flow. You get rid of delta t because we're looking at the equal amount of time. So AV1 equals AV2. So area velocity 1 is equal to area velocity 2. This is called a continuity equation, which says whatever goes in must come out. Fluid is not created or lost inside, right? You have 20 people coming in, 20 people exited. Whatever goes in must also go out, the same amount. So using this continuity equation, you can see that for a steady flow, the bigger the area, the slower the liquid flows, right? Because you can see that bigger the area, the smaller the velocity. Okay, so the smaller the area, more narrow, if your tube becomes more narrow, then you're dealing with a much faster speed of the water stream. Okay, now let's see if we can use that to answer a question. 1 second. Okay, well. Okay, so here is a question. All right. We have a hose, has a diameter of 4 centimeters. If one wants the velocity of the water coming out to be 4 times higher, what should we do? What kind of nozzle should we do at the end of the hose? So this has to do with the continuity equation. This should be fairly straightforward. It's a direct application of the A1 V1 times A2 V2. So I'm going to give you maybe a minute or two to discuss, and then we can vote on this after you come back. All right, let's run the clock for 10 more seconds. I need to update the share. The screen seems to have frozen. All right, I'm gonna go ahead and close this and then we can take a look. 1 second. All right, so the question is asking what is the diameter of the hose that you should use? We want the velocity to come out to be higher, 4 times higher. So if we want the water to flow faster, do we want to make the hose wider or narrower? What do you think? We want it to flow faster, so we wanted to make the diameter bigger or smaller. Make it bigger, you make it more wide. Make it smaller, you make it more narrow. So using the continuity equation, we need to make it smaller. Yes, very good. Yes, thank you all for those who are answering the question. Yes, it's going to be smaller, right? Which the diameter before was 4 centimeters, and you want to make it narrower. That kind of limits you to some of these choices, right? Okay, so if the velocity is 4 times higher, which means the area would be 4 times smaller, right? Because they're proportional. The area to be 4 times smaller, area for a circle is pi r squared. So if the area is 4 times smaller, the radius would be 1/2, right? Because if r becomes 1/2, then area becomes 1/4, 4 times smaller. So area needs to be reduced by half. Radius. Radius is half of the diameter. Diameter also going to be reduced by half, right? So it used to be 4, and now it has to be reduced by half. So it's 2 centimeters. Right now you want to use a 2 centimeters hose. It's going to make the speed to be 4 times of the speed before. So D is correct. All right, so what can we say more about understanding in terms of understanding the continuity equation? We said it's saying the same amount, which is the amount is described by the volume, right? The amount of liquid goes in, comes out. And we're looking at an equal amount of time. So we divided that by the time. So the units will be described by volume per second. So knowing this will tell us how quickly we can fill up a space or with water, or how quickly we can empty a space in water. Right? Because if we know 2 gallons per second, you know that in 1 second, 2 gallons flows in or flows out. It tells you how quickly you can fill something up or empty it. Continuity equation shows up whenever where we have a conserved current. Water current, the same goes in as it goes out. It's a conserved current. Here you have it in the liquid context, but in 1520, you will have it in the electrical current, the flowing of the electricity. You also will have a continuity equation there. All right, so that's a little bit more about the continuity equation. The second thing, for fluid dynamics, we're going to introduce something called Bernoulli's principle, Bernoulli's equation. Okay, so I know there's a lot to focus on here. I'm going to derive the Bernoulli's principle in a separate page so we can do a little slower instead of looking at my animation. So Bernoulli's equation is really derived from conservation of energy. There is nothing new about it or in terms of physics. It is a new format or application, but the underlying principle about it is something you have already learned. It's conservation of energy. So using conservation of energy in the context of fluid flow, So if you're looking at the diagram right here, you have fluid coming, flowing in this direction with different width at different parts of the tube. Area A is a little bit wider, area 2 a little bit more narrow. So if you consider two equal volumes V of water entering and leaving the tube, you can think of this water as a cylinder of water, right? You artificially looking at, okay, this blob of water and this blob of water, they have the same volumes, right? This blob's coming in, this blob of water leaving the tube. The water entering will feel a force from the pressure from the left-hand side, because we say that there is a pressure anywhere inside the liquid or anywhere within our air. But inside the liquid, we're going to have pressure everywhere. So particularly if you're looking at the left-hand side of this blue tube, this blob of water, it's feeling a force from the left-hand side. And that force is equal to P1 times A1 because P is F over area, right? So force 1 is going to be P1 times area 1. So that is pushing the liquid to the right-hand side from the and is from the left-hand side of the volume. And if you push the blob of volume over a certain distance, you're going to do work. So work is going to be force 1 times D1, force times distance, which is P1 A1 times D1. You can see A1 D1 is going to be the volume of this blob of water, so it's just P1 V, the volume, V here. And at the same time, the water, this blob of water leaving the area is going to feel a force as well. Right, that's coming from the right-hand side, is pressing to the left-hand side. And this force, F2, is P2A2, right? And this force is pushing to the left, but your liquid is exiting, is going to the right-hand side, flowing to the right. So the work done by force 2 is actually negative, because force and distance are now not at the same direction. Okay, again, you're not seeing my writing, so I need to go ahead and share my screen again. Okay, so previously what we did is writing the force 1 here as P1A1, right? The work done by force 1, this is a P1, right? It's like there's a force acting on this column of water. Right? At the same time, there's a force from P2 is pushing on this column of water. Right? The work done by force 1 is F1 D1, which is P1 A1 D1. A1 D1 is the volume of the water, is V. The force done by F2 is negative because the water is flowing from left to right. The displacement of this water is to the right-hand side, but the force is pushing from the left-hand side, which is negative. So it gives you a negative work. The negative P2A2 D2, and this is also the volume PV. Okay, so that gives me the energy input and output. So in this case, work 1 will be your energy input, work 2 will be energy output. So energy input minus energy output together is the energy transfer, which is P1V minus P2V. Okay, so that's our E in and E out. So now let's look at what is a final energy versus a motion energy. So this is really just a application of conservation of energy on water flow. Our system, of course, is water stream plus Earth, because we want to be talking about potential energy. So we're going to include Earth in our system. So E final minus E initial equals input minus E output. And this one we just derived right here. So we're going to use it later. We're going to work on the left-hand side. At any given moment, you are dealing with kinetic energy and potential energy of the water system. So you can have kinetic energy final plus potential energy final, and kinetic energy initial, potential energy initial for the initial energy of the system is equal to in minus E out. Okay, so what is the kinetic energy at different locations? So I'm going to say initial and final is location 1 and 2. So potential energy at location 1, or you can say at a particular location, it's going to be M1G/Y1. So the mass of the water times G is the 9.8 meters per second times the height of the water. Okay, Y1 is how high your water is above your reference point. P potential energy at location 2 is M2G/Y2. But noticing that we always want to represent things using the density of the water, so I'm going to replace M1 and M2 using density. So how do I do that? Density is rho 1, rho G, so mass is density times volume, right? Volume G/Y1. We're dealing with the same density, so just rho. M2 is density VG/Y2. Okay, so if the volume are different volume, you have V1, V2, but now we're considering equal amount of volume, so it's just V. We can do kinetic energy and at 2 different locations. Kinetic energy at location 1 is mv1, little v, at location 2 as v2 squared. Okay, m is still the same, 1/2 rho v v1 squared. Here we have 2 different v's. The volume v, I use capital V to represent it. Velocity v, I use little v to represent it, just to be careful. It's to represent one volume and one is velocity. Okay, finally, we are able to combine all of these into this equation and to finally have Bernoulli's equation. So let's put all of these back in here. One second. So we'll have kinetic energy plus potential energy final minus kinetic energy initial plus potential energy initial equals E in and E out. Okay, so I'm going to plug in 1/2. This is my kinetic energy, rho V, capital V, V1 squared, plus potential energy, rho V G/Y1, minus 1/2 rho V V2 plus rho V G/Y2. So this is equal to in and out. That is equal to P1V minus P2V. Oh, 1 second. I'm sorry. I picked initial to be 1 and final to be 2. Okay, so these are initials. These are finals. Okay. So the 2s are kinetic energy 2, potential energy 2 are the finals. Kinetic energy 1, potential energy 1 are initials. Now, it doesn't matter which one you name to be 1 or 2, is that I want it to be consistent with my energy input and output. In this case, I have written the input and output to be input is the positive work, the output is a negative work done by the water from the right hand side. So I have already kept this as this particular order. I assume water flowing from the left to right. So I just need to be consistent. I'm sorry, I put it flipped the other way around earlier. So these are energy final, these are energy initial, and these are the input and output. All right, so we are getting really close. Now, to clean this equation up a little bit, we have, let's cancel all the stuff that we can cancel. We can cancel V from all the side of the equation. P1, P2, there's nothing else we can cancel. So we will have P1, the P1, plus 1/2 rho V1 squared. Okay, this is a negative, so if you move it to the other side, it's plus. What else? You have Y1 negative for plus rho G Y1 is equal to, so P2, move it to the other side, P2 plus 1/2 rho V2 plus rho G Y2. Okay, so this is Bernoulli's principle. Sorry, this is Bernoulli's equation describing the relationship of the pressure inside a water stream or fluid stream with respect to the velocity of the flow as well as the height of the water. So you can see this is really nothing new about physics. This is old physics used in new context. This is conservation of energy, and you plugged in the specific format for these terms and you get a Bernoulli's equation. Okay. I want to say that even though I took some time to derive this, because I want you to see the physics behind these principles. When you're using them, you understand where it's coming from, but we are not requiring you know the derivation. So when we are solving problems, we are doing our homework or exams, is that we're using this equation right away. But we already know where it's coming from. It's coming from the conservation of energy equation. Okay, so we have a Bernoulli's equation. Sorry, it's in principle. It's Bernoulli's equation. Okay. So far for liquid that is a flowing, that is moving, we gave you two equations. One is the continuity equation. One is Bernoulli's equation. Often problems will require you use both of them to solve the problem. What is continuity equations telling you? It's really telling you if you make something wider, it's going to flow slower, right? The more wide it is, the slower it's going to flow. The more narrow it is, it's going to flow faster. Really? That's it. And Bernoulli's equation is a conservation of rewriting conservation of energy using the density times volume instead of mass, accounting for the work done. Okay, so later on we will have an example. But before we do that example, there's one more thing I want to talk about in terms of fluid dynamics. Okay, so these two equations here. So we want to be able to see the application of our fluid dynamics in real life. One thing that we can think of how it's relevant to us, for example, we have airplanes, right? Obviously, that has a lot to do with fluid dynamics. Now we are able to explain lift. So for example, we're able to explain lift using Bernoulli's equation because due to the symmetry of the geometry of the shape, the streamlined shape of your wings, you're creating a difference in terms of the speed of the flow. So you can combine the continuity equation and Bernoulli's equation to explain lift. So how do we do that? Given this particular shape, we're creating air columns flowing on the top of the streamline to be a little bit more narrow than the bottom. So the air that's flowing on the top is going to have a bigger speed. So we have a bigger velocity. And on the bottom, you have a slower velocity, smaller velocity. And also, according to the second equation, wherever you have a bigger velocity, you have a smaller pressure. Okay, so V1, if V1 is smaller, then the pressure is bigger. Here, the velocity is bigger, meaning the pressure is smaller. Below the wing, the pressure is bigger. So you can see we combined the continuity equation and Bernoulli's equation to explain lift. So what happens if the pressure is bigger or smaller? So the pressure from the air pushing on the wing from the top should be pushing it down, and the air from the bottom should be pushing it up. The pressure on the bottom is bigger, so there's more force acting on the bottom than the force acting on the top. So overall, it created the upward force that's giving us the lift of the wing, right? So that explains Bernoulli equation explains how we use the wings on the airplane or sails on the boat, as well as some other stuff that you may have seen in life or not. For example, lift up the ball using a leaf blower. So you may not always have seen it in real life. So let's look at a demo that will show us what I'm talking about.
Fred Smith here told us the B&H photo helped change his life. Fred, tell us your story.
This is a demonstration of Bernoulli's principle. I taught for 24 years in West Virginia, and our home in West Virginia had a heat vent that was on the floor. And so the hot air came up through that vent into the room. And one day the kids had a balloon, and that balloon was balancing in midair above that heat vent. And I thought, how in the world does that work? And it's actually quite interesting. So this is the phenomenon. We've got a stream of air that comes up vertically, in the case of West Virginia, through the heat vent. And then you've got a rather light object, in that case a balloon, in this case a foam ball, that's perched and being balanced and levitated by that stream of air. The principle is that the uprushing air holds the ball up. There's some momentum transfer when the air hits the bottom of the ball, and it holds it up. So that part is not so mysterious. The part that is mysterious, and was to me, was what happens if that ball gets off-centered? So let's say it moves to the left, and this shows the uncentered situation with the ball to the left and the stream of air going past it on the right. Well, why does that ball want to move back into that rushing air? You'd think that it wouldn't want to move back into the air, and it would just fall off to the side. But what happens is that Bernoulli's principle comes into play. Over here, there's a lot of air on the right side that's rushing past the ball. And Bernoulli's principle says that if you have a high velocity, a high airspeed, then you have a low pressure. So this air on this side of the right side of the ball exerts a smaller amount of pressure on this ball than the atmospheric pressure does on the other side. So this arrow represents the atmospheric pressure pushing the ball to the right, and this represents the less than atmospheric pressure that tries to push the ball back to the left. The atmospheric pressure from the left wins and pushes the ball back into the centered configuration, where now you've got equal pressures on each side and the ball is happy. So you can take this up to any scale that you want to, including this rather large scale demonstration. And that is Bernoulli's principle.
All right, so we have just seen a demonstration of Bernoulli's, the application of Bernoulli's equation. There, the different speed are caused by the ball shifting away from the center, right? And now, one side of the ball is still having the hot blowing air through it. Of course, that is a bigger speed, and the other side of the ball is getting close to the normal air in the room, that atmosphere, that has a slower speed, and causing a difference in pressure and causing a difference in force. So that force always dragged the ball into the center if the ball initially had a little bit shift away from the center. That's why you were able to keep it in the sort of holding it in stream like that without it falling. All right, so that's an application. So finally, we have one more example to do to use the Bernoulli's equation. So here we consider a water dam. We have 3 different points, points 1, 2, and 3. And that give us height above the ground. We say 3 has a height of 0, it's at the ground. Point 2, 150 meters above the ground, and point 3 is 200 meters above the ground. And it's also telling us the pipe right here has a radius of 4 meters. And the pipe over here has a radius of half of that. So tell us the width of these pipes. And then it's asking what is the water velocity at 3 and the pressure at 2. So this is the question. All right, so let's try to solve the problem together for the remaining time. If we pick point 1 and 3, we're able to solve for the water speed at point 3. So we're going to use the equation we just derived, P1 plus 1/2 rho V1 plus rho Gy1, P3, another point is 3, 1/2 rho V3 plus rho Gy3, right? That is the Bernoulli's principle, the equation we just derived. So P1 is right at the atmosphere. So P1 is just atmosphere pressure, P0. Water is not flowing at the top, right? It's flowing down. So at the top, it still has 0 speed. So V1 is 0. And Y1 is 200 rho Gy1, 200 meters. P3, you can see over here, is also at atmosphere pressure, because it's not within the center of the liquid. It's here you're exposing it to the atmosphere. So it's P0 as well. And we want to know what is V3, we don't know. And Y3 is 0. Okay, so you can see that we got rho Gy1 equals 1/2 rho V3. Cancel rho. We get velocity 3 is square root of 2Gy1, which is 63 meters per second. Okay, So this is really just the water falling. That is the speed from free fall. And the question asked, what is the pressure at 2? Okay, what is the pressure here? Okay, so you know, okay, if we need to the pressure at 2, let's write Bernoulli's equation for the 2 points, point 1 and point 2. Let's see what we get. So now let's pick 2 different points, point 1 and point 2. So point 1, we already said is P naught plus rho G Y1, right? I've already got this. Now point 2 is P2, pressure at 2, that's one we want to solve, plus 1/2 rho V2 squared plus rho G Y2. So to find the pressure at P2, we need to know V2 because everything else we already know. We just don't know what V2 is. So how do we find V2? Knowing that we oftentimes combine Bernoulli's equation with another equation. What is the other equation? Combined with continuity equation, right? So continuity equation tell us the area and the volume at one place is equal to the area and area and speed at another place. So I'm going to look at area and speed at point 2 versus area and speed at point 3. Okay, I know exactly how wide and how narrow 2 and 3 are, and I can find velocity at 2. So velocity at 2 is A3 over A2, velocity times velocity at 3. Now, this is half of the diameter of this, which means the area is going to be a quarter of the area at location 2. So this is 1/4, a quarter, times velocity at 3, which is we just calculated, is 63. So you get 63 over 4 meters per second. And you can plug that in, you can find your pressure. So to finish this calculation, pressure at point 2 is pressure at atmosphere plus rho Gy1 minus rho Gy2 minus 1/2 rho velocity 2 squared. This is 10 to the 5th Pascal, roughly, right? 100,000 Pascal. Rho is 1,000 kilo per meter cube. G, a lot of times we can just use 9.8 instead of, we can use 10 instead of 9.8. Y1 minus Y2. Y1 is 200, Y2 is 150. So it's going to be this much meters minus 1/2, again, rho times velocity squared. Velocity you have just calculated. So everything plugged in, we get the pressure here at location 2 is 475 Pascal. Okay, so you can see that for fluid dynamics, we introduced 2 equations. One is continuity equation and one is Bernoulli's equation. Okay, continuity equation tells you if you come away with a take-home message is the wider the tube is, the slower it flows. The one sentence summary of the Bernoulli's principle is the faster the flow, the smaller the pressure. So that has to do with the streamlined shape of our car in terms or our wings of the airplane to create a lift, to be taking advantage of the lift that is we can use for fluid dynamics. All right, so that's all. That's all we have to discuss for fluids. I know it's relatively quite a lot of content, but it's really, if I wanted to give you a really quick summary, is for static fluids. We talked about mostly 2 important things. One is the pressure underwater is the pressure at the surface of water from the atmosphere and the pressure from the liquid, rho GH. Okay. The one other thing about the static fluid that's really important, Archimedes principle, saying the force the buoyant force is equal to the weight of the water displaced, so that's rho, the liquid, G times V, okay, the water displaced. So whatever liquid you're talking about, right, that is the buoyant force acting on the object. So static fluid, we have two equations, and dynamic fluid dynamics, we have two equations, that is the continuity equation and Bernoulli's equation. So just those two, just those four are key points that we did for fluids. All right. Okay, so that's all for today. Also, that concludes this entire semester. Well, thanks for all of you who stayed throughout the semester. I know it's not easy, and I know people have, a lot of you stopped coming to class, but for those of you who continue to stay, I really appreciate that your effort, spending the effort. I think that will pay off, certainly pay off in your final outcome of the class. So if you have any questions, feel free to continue to email me or come to Friday's office hour at the different link on Blackboard announcements, or you can chat to me on Tuesday, but please don't wait until last minute. If you have any questions, get it out of the way as soon as possible is the best. And you have one more post assessment. That's for extra credit on Blackboard. And homework are still open until the end of this week. You can still do that, but I think more effort should be spent on preparing for exam rather than making up an old homework set. So that's all I can think of at this point. If I think of anything, I will send out announcements to continue communicating with you. But otherwise, I'll either see you on Friday. If not, I wish you have a good finals week and a good summer, okay? All right, bye everyone.
Thank you,
Thank you,
Professor.
Professor.
Summer.
Bye.